Hello there, and welcome to Sleep Science Chronicles. Tonight, we turn our gaze upward, past the rooftops and the clouds, past the familiar face of the moon, and out into the dark and luminous ocean of space. We are going to explore one of the oldest and most profound questions humanity has ever asked. A question that has stirred the hearts of philosophers, scientists, dreamers, and children, staring at the night sky since the beginning of recorded thought. What if we are not alone? What if, somewhere out there in the vast stretches of the cosmos, life exists beyond our small blue world? Not in the realm of science fiction, but in the quiet, patient reality of the universe itself. What if, on some distant moon or hidden ocean or faraway planet, something is alive right now, breathing, growing, drifting, dreaming in ways we cannot yet imagine? Tonight, we will wander gently through this question. We will explore what science has discovered, what remains unknown, and what possibilities still shimmer at the edges of our understanding. There will be no answers carved in stone. Only wonder, only quiet contemplation, only the soft glow of distant stars inviting us to consider what might be. So settle in. Let your body rest. Let your thoughts slow and soften. You do not need to hold on to every detail. You do not need to remember or analyze. Simply let these ideas drift past you, like clouds across a night sky, and allow yourself to be carried gently into the mystery. The universe is unimaginably large, so large, in fact, that the human mind struggles to grasp it. Our galaxy alone, the Milky Way, contains somewhere between 100 billion and 400 billion stars. And the Milky Way is just one galaxy among hundreds of billions of galaxies scattered across the observable universe. Each of those galaxies holds its own billions of stars, and around many of those stars orbit planets, some rocky, some gaseous, some drifting in the cold dark, and some bathed in the gentle warmth of their parent sun. The numbers are so vast that they lose meaning. Trillions upon trillions of worlds, more planets than grains of sand on all the beaches of Earth. And yet, as far as we know, life has only arisen once, here, on this pale blue dot circling an ordinary yellow star in an unremarkable arm of an average spiral galaxy. Is that possible? Could we truly be alone in all of that immensity? Or is life something that emerges wherever conditions allow? A natural expression of chemistry and time, as inevitable as rivers carving canyons or crystals forming in cooling stone. Tonight, we will explore these questions not with urgency, but with patience. We will begin with life as we know it, the strange and resilient forms that have emerged on Earth. We will journey to the places in our own solar system where life might still be hiding. We will venture further, to distant exoplanets and alien suns, and consider what kinds of life might exist in environments nothing like our own. We will listen for signals from the stars, and wonder why, if life is common, we have not yet heard a single voice calling back to us from the darkness. And we will sit with the mystery, the beautiful, humbling mystery of a universe that may be teeming with life, or may be as silent and empty as it appears. There are no easy answers here, only questions that have haunted humanity for centuries and continue to drive our most ambitious explorations. But perhaps, in the asking, we find something valuable, a reminder of how strange and precious our own existence truly is. Let yourself drift into this cosmic wondering. Let the questions carry you gently toward sleep. And if you wake tomorrow with a renewed sense of wonder at the night sky, then this journey will have served its purpose. And just before we begin, if these calm and curious explorations help you unwind or give your mind a quiet place to rest at the end of the day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do. Simply settle in, breathe softly, and let's begin. The observable universe stretches approximately 93 billion light-years across. This is not the entire universe, only the portion from which light has had time to reach us since the Big Bang. What lies beyond that horizon remains unknown, possibly infinite, possibly containing more galaxies and stars and worlds than we could ever count. When we ask whether life exists elsewhere, we are asking about a canvas so large that our entire planet is smaller than a single atom in comparison to the Earth itself. The scale is not just humbling, it is almost incomprehensible. Within this observable universe, astronomers estimate there are at least 2 trillion galaxies. That number has grown as our telescopes have improved, peering deeper into space and further back in time. Each galaxy is a vast island of stars, gas, dust, and dark matter, drifting through the cosmic void. Some galaxies are small, containing only a few billion stars. Others, like the giant ellipticals, hold trillions. And within each of these stellar cities, planets orbit in numbers we are only beginning to understand. Our own Milky Way galaxy is home to an estimated 100 to 400 billion stars. The uncertainty in that number reflects how difficult it is to count stars hidden behind dust clouds or too faint to detect. But even the lower estimate means there are more stars in our galaxy alone than there are grains of sand in a handful of beach. And around those stars, planets are not rare. They appear to be the rule rather than the exception. For most of human history, we did not know whether planets existed beyond our solar system. The first confirmed exoplanet, orbiting a sun-like star, was discovered in 1995. Since then, the count has exploded. As of recent estimates, astronomers have confirmed more than 5,000 exoplanets, with thousands more candidates awaiting verification. And these are only the ones we have managed to detect with our current technology. A tiny fraction of what must exist. Statistical analyses suggest that, on average, every star in the Milky Way has at least one planet. Some stars have entire systems of planets, like our own Sun with its 8 major worlds and countless smaller bodies. If we take a conservative estimate of 200 billion stars in our galaxy, that means at least 200 billion planets in the Milky Way alone. And the Milky Way is just one of 2 trillion galaxies. When we multiply these numbers, planets per star, stars per galaxy, galaxies in the observable universe, we arrive at estimates so large they are difficult to write. Some calculations suggest there may be more than 10 sextillion planets in the observable universe. That is a 1 followed by 22 zeros. More planets than all the grains of sand on every beach on Earth. More worlds than seconds that have passed since the Big Bang. Among all these planets, how many might be suitable for life? This is where the question becomes more difficult. Not every planet is hospitable. Many are too hot, too cold, too close to their star, too far away, too large, too small, or lacking the necessary chemistry. But even if only a tiny fraction of planets meet the conditions for life, the sheer number of worlds means that fraction could still represent billions or trillions of potentially habitable places. The Drake equation is a famous attempt to estimate the number of active, communicative civilizations in our galaxy. It was formulated in 1961 by astronomer Frank Drake, not as a precise calculation, but as a way of organizing our ignorance. The equation multiplies together factors like the rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction where life actually emerges, and so on. The result depends entirely on what values you assign to each factor, and most of those values remain unknown. Optimistic estimates using the Drake equation suggest there could be thousands or even millions of civilizations in the Milky Way alone. Pessimistic estimates suggest we might be the only one. The equation does not give us an answer. It gives us a framework for thinking about the question, and it reminds us how much we still do not know. One of the most striking realizations of modern astronomy is that the ingredients for life are everywhere. The elements that make up living things on Earth, carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, are among the most common elements in the universe. They are forged in the hearts of stars and scattered across space when those stars explode. Every planet, every moon, every asteroid is built from this same cosmic material. Water, too, is remarkably common. Once thought to be rare and precious, water has been found throughout the solar system and beyond. It exists as ice on moons and comets, as vapor in planetary atmospheres, and possibly as liquid oceans beneath frozen surfaces. The building blocks of life are not unique to Earth. They are woven into the fabric of the cosmos itself. This does not mean life is inevitable. Having the right ingredients is not the same as having a finished recipe. The transition from chemistry to biology, from molecules to living cells, remains one of the deepest mysteries in science. We do not yet know how life began on Earth, let alone whether that process could repeat itself elsewhere. But the ubiquity of life's raw materials suggests that if life can arise from chemistry, it has had countless opportunities to do so across the universe. The question of alien life is not merely scientific. It is philosophical, even spiritual. It touches on our deepest ideas about meaning, purpose, and our place in the cosmos. If life is common, what does that say about our significance? If life is rare, what responsibility does that place on us? These are questions that science alone cannot answer, but science can illuminate the landscape in which we ask them. To search for life elsewhere, we must first understand life here. Earth is the only place in the universe where we know life exists. Every microbe, plant, animal, and fungus on this planet shares a common ancestor, a single origin of life that arose billions of years ago and diversified into the astonishing variety we see today. This is both our greatest source of knowledge and our greatest limitation. We have exactly one example to study. Life on Earth is based on carbon chemistry. Carbon atoms have a unique ability to form complex molecules by bonding with themselves and with other elements like hydrogen, oxygen, and nitrogen. This versatility allows carbon to build the long chains and intricate structures that make up proteins, DNA, and the membranes of cells. All known life shares this carbon-based foundation. Water is equally essential. It serves as the solvent in which life's chemistry takes place, allowing molecules to move, interact, and react. Water has unusual properties that make it ideal for this role. It remains liquid over a wide temperature range. It dissolves a remarkable variety of substances, and it expands when it freezes, allowing ice to float and insulate the liquid water beneath. Life on Earth is water-based through and through. The genetic code of all known life is written in DNA, or its close relative, RNA. These molecules store information in sequences of chemical bases, like letters in an alphabet. The same genetic code is used by bacteria, trees, insects, and humans, a powerful clue that all life on Earth descends from a single common ancestor. This universality is both elegant and limiting. We do not know if other forms of information storage might work elsewhere. Life appeared on Earth remarkably quickly. The planet formed about 4.5 billion years ago, and for its first several hundred million years, it was bombarded by asteroids and comets in a violent period called the Late Heavy Bombardment. Yet fossil evidence suggests that microbial life was present by at least 3.5 billion years ago, and possibly earlier. Life did not wait. It emerged almost as soon as conditions allowed. This rapid emergence is one of the strongest arguments for the idea that life might be common in the universe. If life took billions of years to arise on Earth, we might conclude that it was a fluke, an improbable accident. But the fact that it appeared so quickly suggests that the transition from chemistry to biology may not be as difficult as we once thought. Perhaps, given the right conditions, life is almost inevitable. For most of Earth's history, life was microscopic. Single-celled organisms dominated the planet for nearly 3 billion years before complex multicellular life appeared. Even today, bacteria and archaea make up the vast majority of life's diversity and biomass. The large animals and plants we see around us are relative newcomers, evolutionary experiments built on billions of years of microbial innovation. This has implications for the search for alien life. If we find life elsewhere, it is far more likely to be microbial than intelligent. Simple life may be common. Complex life may be rare. The universe could be teeming with bacteria-like organisms while remaining silent of civilizations. This is not a disappointing possibility. It is a profound one. Even the discovery of a single alien microbe would revolutionize our understanding of life's place in the cosmos. Life on Earth has survived catastrophic events that would seem to make existence impossible. Asteroid impacts, supervolcano eruptions, ice ages, and mass extinctions have repeatedly devastated the biosphere, yet life has persisted. Each time, it has recovered and diversified anew. This resilience suggests that once life takes hold, it is remarkably difficult to eradicate completely. The history of life on Earth is also a history of transformation. Life has fundamentally altered the planet it inhabits. Photosynthetic organisms filled the atmosphere with oxygen, rusting the iron in the oceans and creating the air we breathe today. Plants colonized the land and changed the climate. Animals burrowed into sediments and reshaped the seafloor. Life is not a passive passenger on Earth. It is an active force that shapes its own environment. If life transforms its environment on Earth, might it do the same elsewhere? This is the basis of the search for biosignatures, chemical or physical signs that life has altered a planet's atmosphere or surface. An oxygen-rich atmosphere, for example, would be difficult to maintain without photosynthesis, continuously replenishing it. Detecting such signatures on a distant world could be evidence of life, even if we never see the organisms themselves. Life on Earth exists in a dizzying variety of forms, from whales to bacteria, from redwoods to fungi, from insects to deep-sea worms. The creativity of evolution seems boundless. Yet all this diversity is built on the same fundamental chemistry. We do not know if life elsewhere would use the same toolkit, or if it might find entirely different solutions to the challenges of survival and reproduction. Some scientists speculate about alternative biochemistries, life based on silicon instead of carbon, or using ammonia or methane instead of water as a solvent. These ideas are theoretically possible, but remain unproven. Silicon can form complex molecules, but not with the same versatility as carbon. Ammonia and methane are liquids at much colder temperatures than water, which could slow chemical reactions dramatically. Still, the universe is vast, and we should be cautious about assuming that life must look like us. The diversity of life on Earth reminds us to expect the unexpected. Evolution has produced creatures that fly, creatures that glow, creatures that survive boiling water and freezing cold. If life can be so creative on one planet, what wonders might it have produced on others? The possibilities are limited only by the laws of physics and chemistry, and perhaps not even by those. One of the most surprising discoveries of recent decades is the existence of extremophiles, organisms that thrive in conditions once thought to be completely inhospitable to life. These creatures have expanded our understanding of where life can survive, and by extension, where it might exist elsewhere in the universe. Deep beneath the ocean's surface, where sunlight never reaches, hydrothermal vents spew superheated water laden with chemicals from the Earth's interior. The water at these vents can exceed 300 degrees Celsius, kept liquid only by the immense pressure of the deep sea. Yet these vents are oases of life. Bacteria and archaea thrive on the chemical energy of the vents, and entire ecosystems of worms, crabs, and other creatures have evolved to depend on them. The discovery of hydrothermal vent communities in the late 1970s revolutionized our understanding of life. Before then, all known ecosystems ultimately depended on sunlight, either directly through photosynthesis or indirectly through food chains. The vent communities showed that life could be powered by chemical energy from the Earth itself, a process called chemosynthesis. This opened the possibility that life might exist on worlds too far from their stars for sunlight to matter. Some microbes can survive extreme heat. The current record holder, a type of archaea called Methanopyrus candleri, can grow at temperatures up to 122 degrees Celsius. At these temperatures, most proteins would unfold, and most cells would be destroyed. Yet these heat-loving organisms have evolved special proteins and cellular structures that remain stable even in boiling water. At the other extreme, some organisms survive in ice. Bacteria have been found living in Antarctic ice cores, persisting in tiny pockets of liquid water between ice crystals. These psychrophiles, or cold-loving organisms, have adapted to temperatures far below freezing, slowing their metabolism to a crawl, but continuing to survive. Some may have been frozen for millions of years, waiting patiently for conditions to change. Life has also been found in environments of extreme acidity and alkalinity. The Rio Tinto in Spain flows red with iron and sulfuric acid, with a pH similar to battery acid, yet microbial life thrives in its waters. At the other end of the spectrum, soda lakes like those in East Africa have pH levels above 10, strongly alkaline, yet they support unique ecosystems of bacteria and flamingos. The deep subsurface of the Earth hosts a hidden biosphere that may contain more biomass than all life on the surface. Bacteria have been found living in rock formations kilometers underground, surviving on trace amounts of hydrogen and other chemicals seeping from the rock. These organisms live in complete isolation from the sun, cut off from the surface world, yet they persist in the darkness. Some extremophiles can survive intense radiation. The bacterium Deinococcus radiodurans can withstand doses of radiation thousands of times higher than would kill a human. It accomplishes this feat through remarkably efficient DNA repair mechanisms, stitching its shattered genetic material back together after exposure. This ability might allow life to survive in environments with high radiation, such as the surfaces of planets without protective atmospheres. Tardigrades, also known as water bears, are microscopic animals famous for their ability to survive almost anything. They can endure extreme temperatures, intense radiation, the vacuum of space, and pressures greater than those in the deepest ocean trenches. When conditions become too harsh, tardigrades enter a state called cryptobiosis, essentially shutting down their metabolism and waiting until conditions improve. The existence of extremophiles on Earth suggests that life is far more adaptable than we once imagined. If organisms can thrive in boiling acid, freezing ice, and crushing depths on our planet, perhaps they could survive the harsh conditions on other worlds as well. The red deserts of Mars, the ice-covered oceans of Europa, the methane lakes of Titan, all seem less impossible when we consider what life has already accomplished here. Extremophiles have also challenged our assumptions about the limits of habitability. The traditional definition of a habitable zone, the region around a star where liquid water can exist on a planet's surface, may be too narrow. If life can survive deep underground or in ice-covered oceans, then habitable worlds might be far more numerous than we thought. The study of extremophiles has practical implications for the search for life. By understanding how organisms survive extreme conditions on Earth, scientists can better predict where to look for life elsewhere and what kinds of biosignatures it might leave behind. Each new extremophile discovered is a lesson in the creativity and persistence of life. Some researchers speculate about a shadow biosphere, the possibility that life arose more than once on Earth, and that organisms with a different biochemistry might still exist, undetected, in extreme environments. This idea remains unproven, but it reminds us that even our own planet may hold surprises. We have not finished exploring the diversity of life on Earth, let alone the diversity that might exist elsewhere. The extremophiles of Earth are ambassadors of possibility. They whisper that life is tenacious, adaptable, and endlessly inventive. They encourage us to look beyond our assumptions and to search for life in places we might once have dismissed as too hot, too cold, too acidic, or too strange. Before we can search for life elsewhere, we must grapple with a surprisingly difficult question: what is life? Despite centuries of study, there is no universally accepted definition. Life is one of those concepts that we recognize intuitively, but struggle to define precisely. Most definitions of life include certain characteristics: the ability to grow, reproduce, respond to the environment, and maintain internal stability. Living things metabolize. They take in energy and materials from their surroundings and use them to sustain themselves. They evolve over generations, changing in response to selective pressures. But each of these criteria has exceptions and edge cases. Viruses, for example, blur the boundaries of life. They cannot reproduce on their own. They must hijack the machinery of living cells to make copies of themselves. They do not metabolize in the traditional sense, yet they evolve, they have genetic material, and they interact with the living world in profound ways. Are viruses alive? Scientists disagree, and the answer may depend more on how we choose to define our terms than on any objective truth. Fire grows, consumes fuel, responds to its environment, and can even reproduce by spreading. Yet we do not consider fire to be alive. Crystals grow and can create copies of their structure, yet they too are not alive. These examples illustrate the difficulty of finding a definition that includes everything we intuitively consider life, while excluding everything we do not. One influential definition comes from NASA, crafted specifically to guide the search for extraterrestrial life. NASA defines life as a self-sustaining chemical system capable of Darwinian evolution. This definition emphasizes two key features: metabolism, self-sustaining chemistry, and evolution, the ability to change over generations in response to selection. It is broad enough to include life very different from our own, yet specific enough to be useful. But even this definition has limitations. How do we detect Darwinian evolution on a distant world? We might find organic molecules or unusual chemistry, but demonstrating that something is actively evolving would require observations over many generations. Potentially impossible for slow reproducing or long-lived organisms. Some scientists argue that we should focus not on defining life, but on detecting it. Rather than asking what life is, we should ask what life does, what observable effects it has on its environment. This pragmatic approach guides the search for biosignatures, chemical, physical, or geological traces that life leaves behind. The philosopher Carol Cleland has argued that attempting to define life with only one example is like trying to define water with only one sample. If ancient scientists had only encountered ice, they might have concluded that water is a solid, cold substance. Only by studying water in its many forms, liquid, vapor, ice, could they arrive at a complete understanding. Similarly, we may need to discover life elsewhere before we can truly understand what life is. This uncertainty is humbling, but it is also exciting. It means that the search for extraterrestrial life is not just a search for organisms like those we know. It is a search for the full range of what life could be. A category that might be far stranger and more varied than we currently imagine. Some theorists speculate about life based on entirely different chemistries. Silicon-based life is a popular idea in science fiction, since silicon can form complex molecules, somewhat like carbon. However, silicon bonds are less stable and less versatile than carbon bonds, making complex silicon biochemistry more difficult. Still, on a cold world with different chemistry, who knows what might be possible? Others have proposed life based on alternative solvents. If water is essential for life on Earth, because it allows chemistry to happen in liquid form, might other liquids serve the same purpose elsewhere? Ammonia, for example, is liquid at much colder temperatures and could potentially support biochemistry on frigid worlds. Methane and ethane, liquid on the surface of Titan, are other candidates. There is also the possibility of life that is not chemical at all, at least not in the traditional sense. Some physicists have speculated about life based on plasma, the fourth state of matter, which exists in stars and interstellar space. Others have imagined life in the form of organized patterns in magnetic fields or other exotic structures. These ideas are highly speculative, but they remind us that the universe may contain possibilities we have not yet conceived. The search for extraterrestrial life is, in part, a search for the limits of life itself. Each new environment we explore, each new form of extremophile we discover, expands our understanding of what is possible. And somewhere out there, on a world we have not yet seen, life may have found solutions to survival that would astonish us. For now, we search with the tools and concepts we have, guided by what we know from Earth. But we do so with humility, aware that life, whatever it truly is, may be more creative and more persistent than we have dared to imagine. When astronomers search for planets that might harbor life, they often begin with a concept called the habitable zone. This is the region around a star where temperatures are just right, not too hot and not too cold, for liquid water to exist on a planet's surface. Because this range of distances resembles the conditions in a familiar fairy tale, it is sometimes called the Goldilocks zone. The habitable zone is not a fixed distance. It depends on the size and temperature of the star. Around a hot, bright star, the habitable zone lies far away, where the intense radiation is diluted by distance. Around a cool, dim red dwarf, the habitable zone hugs close to the star, where a planet can gather enough warmth to keep water liquid. Each star has its own Goldilocks region, and the planets that orbit within it are considered prime candidates in the search for life. Earth sits comfortably within the Sun's habitable zone. We are not too close, like Mercury, where temperatures soar high enough to melt lead. We are not too far, like the outer planets, where the Sun appears as little more than a bright star, and water exists only as ice. Our distance from the sun allows oceans to remain liquid, clouds to form, and rain to fall. It is one of the reasons life has flourished here for billions of years. But the habitable zone is not a guarantee of habitability. A planet can orbit at the right distance and still be utterly lifeless. Mars, for example, sits at the outer edge of the sun's habitable zone, yet its surface today is a frozen desert with an atmosphere too thin to support liquid water. Venus orbits closer to the inner edge and has become a hellish world with surface temperatures hot enough to melt lead, despite being nearly Earth's twin in size. The presence of an atmosphere matters enormously. An atmosphere can trap heat through the greenhouse effect, warming a planet beyond what its distance from the star would suggest. Earth's atmosphere keeps us warmer than the moon, which sits at the same distance from the sun, but has no air to hold on to heat. Too much greenhouse effect, however, and a planet can overheat, as Venus demonstrates so dramatically. A planet's size also plays a role. Small planets may lack the gravity to hold onto an atmosphere, allowing gases to escape into space over millions of years. Large planets may retain thick atmospheres of hydrogen and helium, creating crushing pressures and strange chemistries unlike anything on Earth. The ideal size for habitability seems to be somewhere in between, large enough to hold an atmosphere, small enough to have a solid surface. Magnetic fields offer another layer of protection. Earth's magnetic field shields us from the solar wind, a stream of charged particles flowing from the sun that would otherwise strip away our atmosphere and bombard the surface with radiation. Mars once had a magnetic field, but it faded long ago, leaving the planet vulnerable. Some scientists believe this loss contributed to the disappearance of Mars's once thicker atmosphere and any liquid water that may have flowed on its surface. The habitable zone concept has evolved over time. Originally, it focused narrowly on surface conditions. Could liquid water exist in the open air? But the discovery of extremophiles on Earth and the possibility of subsurface oceans on icy moons have expanded our thinking. Life might thrive far outside the traditional habitable zone, warmed by internal heat rather than starlight, hidden beneath miles of ice. Some researchers now speak of a galactic habitable zone as well. This is the region within a galaxy where conditions favor the development of life. Not too close to the violent center, where radiation and stellar encounters are frequent, and not too far in the sparse outer regions, where heavy elements needed for rocky planets and complex chemistry are scarce. The sun sits within this galactic sweet spot, another factor that may have contributed to Earth's habitability. The search for habitable exoplanets has accelerated in recent years. Space telescopes like Kepler and TESS have discovered thousands of planets, many of them orbiting within their stars' habitable zones. Some are rocky worlds roughly the size of Earth. Others are larger, so-called super-Earths, whose properties remain uncertain. Each discovery adds to a growing catalogue of places where life might, just possibly, have taken hold. Not all stars make good hosts for habitable planets. Red dwarfs, the most common type of star in the galaxy, present particular challenges. Because they are dim, their habitable zones lie very close to the star. Planets in these tight orbits often become tidally locked, with one side perpetually facing the star in eternal daylight, and the other side frozen in endless night. Whether life could adapt to such extreme conditions remains an open question. Red dwarfs are also prone to violent flares, sudden outbursts of radiation that could sterilize the surface of any nearby planet. A world orbiting a red dwarf might need a thick atmosphere or a strong magnetic field to survive these outbursts. Some scientists remain optimistic about red dwarf habitability, while others suspect that these small, temperamental stars may be hostile to life. The concept of the habitable zone is a useful starting point, but it is not the final word. Life is more adaptable than we once assumed, and the universe is more varied. The search for habitable worlds continues to expand, guided by new discoveries and a growing appreciation for the many ways a planet might become a home for life. Water is essential to life as we know it. It is the medium in which the chemistry of life takes place, the solvent that allows molecules to meet and react, the substance that fills our cells and flows through our veins. When scientists search for life beyond Earth, they often follow the water, seeking places where this precious liquid might exist. Water is surprisingly common in the universe. It forms easily from hydrogen and oxygen, two of the most abundant elements in the cosmos. Water has been detected in interstellar clouds, in the atmospheres of distant planets, in the tails of comets, and in the icy crusts of moons. The raw materials for water are everywhere. The challenge is finding places where it remains liquid. On Earth, liquid water exists because of our distance from the sun, our atmosphere, and our planet's internal heat. But Earth is not the only place in the solar system where liquid water might be found. Some of the most exciting targets in the search for life are not planets at all, but moons, icy worlds orbiting the giant planets of the outer solar system, where vast oceans may lie hidden beneath frozen shells. Europa, a moon of Jupiter, is one of the most tantalizing destinations in the search for extraterrestrial life. Slightly smaller than Earth's moon, Europa is covered in a shell of ice that gleams white and is crisscrossed with reddish-brown streaks. Beneath that ice, scientists believe, lies a global ocean of liquid water, more water, in fact, than all the oceans of Earth combined. The evidence for Europa's ocean comes from several sources. The moon's surface is remarkably smooth and young, suggesting that it is constantly being resurfaced by processes below. The icy shell appears to shift and crack in ways that imply a liquid layer beneath, and measurements from spacecraft have detected induced magnetic fields consistent with a salty, conductive ocean hidden under the ice. Europa's ocean is kept liquid not by sunlight, but by tidal heating. As Europa orbits Jupiter, the giant planet's immense gravity squeezes and stretches the moon, generating friction and heat within its interior. This internal warmth is enough to maintain liquid water, despite the frigid temperatures of the outer solar system. It is a reminder that habitability does not require proximity to a star. If Europa's ocean exists, it has likely been there for billions of years, long enough for life to potentially arise and evolve. The ocean is in contact with a rocky seafloor, which could provide the minerals and chemical energy that life requires. Hydrothermal vents, like those found on Earth's ocean floor, might exist on Europa, creating oases of warmth and chemistry in the cold darkness. Ganymede, the largest moon in the solar system, may also harbor a subsurface ocean. This moon of Jupiter is even larger than the planet Mercury, and evidence suggests it has a layered interior with a liquid water ocean sandwiched between layers of ice. Ganymede's ocean lies deeper than Europa's, making it harder to access, but it adds another potential habitat to our growing list. Callisto, another of Jupiter's large moons, rounds out the trio of possible ocean worlds in the Jovian system. Callisto's surface is ancient and heavily cratered, but measurements hint at a liquid layer beneath. If confirmed, it would mean that 3 of Jupiter's 4 largest moons, discovered by Galileo over 4 centuries ago, might each contain hidden oceans. Saturn's moon Enceladus has emerged as one of the most exciting targets in the search for life. This small, icy world is only about 500 kilometers across, yet it has captured the attention of scientists around the world. The reason is dramatic. Enceladus is actively venting water into space. Near its south pole, Enceladus has a series of fractures nicknamed tiger stripes. From these cracks, plumes of water vapor and ice particles erupt into space, shooting hundreds of kilometers above the surface. The Cassini spacecraft flew through these plumes and analyzed their composition, finding water, organic molecules, and salts consistent with a subsurface ocean in contact with rock. The discovery of hydrothermal activity on Enceladus was particularly exciting. Cassini detected tiny grains of silica in the plumes, a mineral that forms when hot water interacts with rock. This suggests that Enceladus has hydrothermal vents on its ocean floor, similar to those that support life in Earth's deep oceans. The little moon has all the ingredients we associate with habitability: liquid water, organic chemistry, and a source of energy. Titan, Saturn's largest moon, offers a different kind of water world. Titan is the only moon in the solar system with a thick atmosphere, a hazy orange shroud of nitrogen and methane that obscures its surface. Beneath those clouds lies a landscape of hydrocarbon lakes and rivers, not water, but liquid methane and ethane, pooling in basins and carving channels through icy terrain. But Titan may also have a water ocean hidden deep below its icy crust. Evidence from the Cassini mission suggests that the moon's interior contains a layer of liquid water, perhaps mixed with ammonia, sandwiched between the icy surface and a rocky core. This ocean is buried far beneath the surface, but it adds Titan to the list of potential ocean worlds in our solar system. The icy moons of the outer solar system have transformed our understanding of where life might exist. A generation ago, the search for habitable environments focused on planets within the traditional habitable zone. Now we know that liquid water can persist far from any star, warmed by the gravitational embrace of giant planets. The ocean worlds of Jupiter and Saturn are among the most promising places to search for life beyond Earth. Mars has captivated human imagination for centuries. Its reddish glow in the night sky earned it the name of the Roman god of war, and its relatively close proximity to Earth has made it a target of fascination and exploration. Of all the worlds in our solar system, Mars has been studied most intensively for signs of life, past or present. Early telescopic observations of Mars fueled speculation about an inhabited world. In the late 19th century, the astronomer Giovanni Schiaparelli reported seeing channels on the Martian surface, which he called canali. This Italian word was mistranslated into English as canals, suggesting artificial waterways built by intelligent beings. The idea of a Martian civilization captured the public imagination and inspired countless works of science fiction. We now know that the canals of Mars were optical illusions, tricks of perception when viewing a distant world through imperfect telescopes. But the fascination with Mars as a potential abode of life has never faded. Modern spacecraft have revealed a world that was once very different from the cold, dry desert we see today. Billions of years ago, Mars was warmer and wetter. Rivers carved channels across its surface, and lakes pooled in craters and basins. The evidence is written in the rocks: ancient riverbeds, sedimentary layers, minerals that form only in the presence of water. Early Mars had a thicker atmosphere and conditions that might have been suitable for life. What happened to Mars? The planet is smaller than Earth and cooled more quickly, losing its internal heat and its magnetic field. Without a magnetic shield, the solar wind stripped away much of the atmosphere. As the atmosphere thinned, temperatures dropped, and liquid water became unstable on the surface. Mars transformed from a potentially habitable world into the frozen desert we see today. But water has not vanished entirely from Mars. Ice exists at the poles, forming bright white caps of frozen water and carbon dioxide. Ice also lies hidden beneath the surface in many regions, preserved by the cold temperatures and low atmospheric pressure. Some scientists believe that liquid water might still exist underground, in aquifers warmed by geothermal heat, or kept liquid by dissolved salts. The search for life on Mars has evolved over decades. The Viking landers of the 1970s carried experiments designed to detect microbial life in Martian soil. The results were ambiguous. Some experiments produced positive signals, but most scientists concluded that the reactions were caused by unusual soil chemistry rather than biology. The question of life on Mars remained open. More recent missions have focused on understanding Mars's past habitability rather than detecting life directly. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have explored ancient lakebeds, analyzed rock compositions, and searched for organic molecules. The picture that has emerged is of a planet that was once capable of supporting life, at least in certain times and places. Curiosity discovered organic molecules in Martian rocks, carbon-containing compounds that are the building blocks of life. This does not prove that life existed on Mars, since organic molecules can also form through non-biological processes. But it demonstrates that the chemistry necessary for life was present on ancient Mars. Perseverance is currently exploring Jezero Crater, a site that was once a lake fed by a river delta. The rover is collecting rock samples that will eventually be returned to Earth for detailed analysis. These samples may contain fossils of ancient Martian microbes, preserved in sediments laid down billions of years ago. Or they may show that Mars, despite its potential, remained lifeless. Either answer would be profound. The possibility of present-day life on Mars is more controversial. The surface is harsh, cold, dry, and bathed in ultraviolet radiation. But life might survive underground, in caves or aquifers where conditions are more stable. Some scientists have speculated about microbial communities living deep below the surface, isolated from the hostile conditions above. Methane in the Martian atmosphere has added intrigue to this possibility. On Earth, methane is produced primarily by living organisms, though it can also come from geological processes. Spacecraft and telescopes have detected traces of methane in the Martian atmosphere, and its abundance seems to vary with location and season. The source of this methane remains unknown. It could be geological, or it could, just possibly, be biological. The search for life on Mars continues with each new mission. Future expeditions may drill beneath the surface, explore caves, or return samples for analysis in Earth's laboratories. Mars remains the most accessible world beyond Earth, where life might have arisen, and our exploration of the red planet is far from over. Venus might seem like the last place to look for life. Its surface is an inferno, with temperatures averaging around 460 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is 90 times that of Earth, equivalent to being nearly a kilometer underwater. Thick clouds of sulfuric acid shroud the planet in perpetual gloom. Yet some scientists believe Venus deserves a closer look. Venus was not always a hellish world. Billions of years ago, it may have been much more Earth-like. Computer models suggest that early Venus could have had liquid water on its surface, moderate temperatures, and conditions suitable for life. If life arose during this clement period, it might have adapted as conditions changed, retreating to habitats that remained hospitable. The surface of Venus is inhospitable today, but the atmosphere tells a different story. About 50 kilometers above the surface, conditions become remarkably mild. Temperatures hover around room temperature, and the pressure is similar to Earth's surface. The clouds still contain sulfuric acid, which poses challenges for Earth-like life. But some extremophiles on our planet thrive in acidic environments. In 2020, a team of scientists announced the detection of phosphine in the atmosphere of Venus. Phosphine is a molecule made of one phosphorus atom and 3 hydrogen atoms, and on Earth, it is produced primarily by living organisms or industrial processes. Finding phosphine on Venus sparked excitement and controversy. Could it be a sign of life in the Venusian clouds? The phosphine detection remains disputed. Other scientists have questioned the analysis, suggesting that the signal might be an artifact of data processing or that other molecules might explain the observations. If phosphine is present, it might also have non-biological sources that we do not yet understand. The debate continues, and future missions to Venus may help resolve the question. The idea of life in the clouds of Venus is not new. In the 1960s, the astronomer Carl Sagan speculated about organisms floating in the Venusian atmosphere, carried by winds and feeding on sunlight or atmospheric chemicals. Such life would be unlike anything on Earth, adapted to an aerial existence in a world of acid and heat. It remains a speculative possibility, but one that scientists take seriously enough to investigate. Several missions to Venus are planned or under development. NASA's Da Vinci mission will send a probe plunging through the Venusian atmosphere, analyzing its composition on the way down. The Veritas mission will map the surface from orbit, studying the planet's geology and history. The European Space Agency's Envision mission will also study Venus in detail. These missions may not find life, but they will help us understand whether Venus was ever habitable and whether its clouds might shelter something unexpected. Venus is a cautionary tale about planetary evolution. It is similar to Earth in size and composition, yet it followed a very different path. Understanding why Venus became a furnace, while Earth remained temperate, helps us appreciate the fragility of habitability. It also reminds us that even hostile worlds may harbor surprises. The search for life in our solar system extends to worlds both familiar and strange. Mars and Venus, our nearest planetary neighbors, each offer different lessons about habitability. One was once wet and warm, then lost its water to space. The other may have started Earth-like, but succumbed to a runaway greenhouse effect. Both remain targets of exploration, and both might yet yield discoveries that transform our understanding of life in the universe. Beyond our solar system, the universe unfolds in staggering abundance. For most of human history, we could only wonder whether other stars had planets of their own. Now we know that planets are everywhere. They orbit stars of all types, in configurations both familiar and bizarre. The discovery of exoplanets, planets beyond our sun, has transformed our understanding of the cosmos and reinvigorated the search for life. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995. It was found not by direct imaging, but by a subtle wobble in the star's motion, caused by the gravitational tug of an orbiting planet. This world, designated 51 Pegasi b, turned out to be a gas giant larger than Jupiter, orbiting scorchingly close to its star. It was nothing like the planets in our solar system, and it hinted at the diversity that lay waiting to be discovered. Since that first detection, the count of known exoplanets has grown to more than 5,000, with thousands more candidates awaiting confirmation. Each discovery adds to a growing catalogue of alien worlds, revealing patterns and surprises that challenge our assumptions about how planetary systems form and evolve. The Kepler Space Telescope, launched in 2009, was a watershed moment in exoplanet science. Kepler stared at a single patch of sky for years, monitoring the brightness of over 150,000 stars. When a planet passes in front of its star, it blocks a tiny fraction of the starlight, causing a brief dimming. By detecting these transits, Kepler discovered thousands of planets and revealed that small, rocky worlds are common throughout the galaxy. One of Kepler's most profound findings was that planets outnumber stars. Statistical analysis of Kepler's data suggests that nearly every star in the Milky Way has at least one planet, and many have multiple worlds. The galaxy is not a sparse scattering of isolated stars, but a dense tapestry of planetary systems, each with its own unique architecture. Kepler also found that planets come in sizes not represented in our solar system. Super-Earths, rocky planets larger than Earth but smaller than Neptune, are among the most common types of planets in the galaxy. We have no local example to study, yet they appear to be everywhere. Their properties remain mysterious. Are they scaled-up versions of Earth, or something entirely different? Mini-Neptunes, planets with thick gaseous envelopes surrounding rocky cores, are also abundant. These worlds blur the line between rocky planets and gas giants. Some may have surfaces buried deep beneath crushing atmospheres. Others might be ocean worlds, with vast seas of water or other liquids covering their entire surface. The diversity of exoplanets exceeds anything we imagined. The TESS mission, launched in 2018, continues the search for transiting planets. Unlike Kepler, which focused on a single region, TESS surveys nearly the entire sky, looking for planets around the nearest and brightest stars. These nearby worlds are easier to study in detail, making TESS discoveries prime targets for follow-up observations. Some exoplanets orbit within their stars' habitable zones, where liquid water might exist on the surface. Kepler 442b, for example, is a rocky world slightly larger than Earth, orbiting a star cooler than the Sun, at a distance that places it squarely in the habitable zone. We know almost nothing else about this planet. Whether it has an atmosphere, whether it has water, whether it could support life. But its existence proves that Earth-sized worlds in habitable zones are real. The TRAPPIST-1 system has captured particular attention. This small, cool, red dwarf star hosts 7 Earth-sized planets, at least 3 of which orbit within the habitable zone. The planets are packed so tightly that from the surface of one, you could see the others as large as the moon in Earth's sky. The system is a laboratory for comparative planetology, offering multiple worlds to study in a single place. But proximity to a habitable zone does not guarantee habitability. The TRAPPIST-1 planets are tidally locked, with one side always facing the star and the other in permanent darkness. The star itself is prone to flares that could strip away atmospheres and sterilize surfaces. Whether any of these worlds could support life remains unknown, but they offer a tantalizing glimpse of what the galaxy holds. Direct imaging of exoplanets remains extraordinarily difficult. Stars are billions of times brighter than their planets, overwhelming the faint glow of reflected light. It is like trying to see a firefly next to a searchlight from miles away. Yet advances in technology have made direct imaging possible for some large, young planets orbiting far from their stars. The images are crude, often just a few pixels, but they represent light that has traveled across interstellar space from an alien world. The next generation of telescopes promises to revolutionize exoplanet science. The James Webb Space Telescope, launched in 2021, can analyze the atmospheres of some exoplanets by studying the starlight that filters through them during transits. By identifying the chemical fingerprints of gases like water vapor, carbon dioxide, and methane, Webb can begin to characterize the atmospheres of distant worlds. Future telescopes may go even further. Proposed missions aim to directly image Earth-like planets around nearby stars, blocking out the starlight with sophisticated instruments called coronagraphs or star shades. Such observations could reveal not just the existence of these worlds, but their colors, their atmospheres, and perhaps even signs of life. The diversity of exoplanets challenges our assumptions about habitability. Hot Jupiters, gas giants orbiting closer to their stars than Mercury does to the Sun, were the first type of exoplanet discovered, and remain among the strangest. Their atmospheres are furnaces of exotic chemistry, with clouds of vaporized rock and winds that howl at thousands of kilometers per hour. Life as we know it could not survive there. But they remind us how varied planets can be. Rogue planets drift through the galaxy without any star at all. Ejected from their birth systems by gravitational interactions, these worlds wander the darkness between stars. Without starlight to warm them, their surfaces are frozen wastelands. Yet if they retain internal heat, they might harbor subsurface oceans, carrying potential habitats through the cosmic void. Water worlds may be common among exoplanets. These are planets with so much water that their entire surfaces are covered in global oceans, potentially hundreds of kilometers deep. At the bottom of such oceans, the pressure would be so great that water transforms into exotic forms of ice, even at high temperatures. Whether life could arise on such worlds is unknown, but they represent a category of planet unlike anything in our solar system. Some exoplanets orbit binary stars, circling two suns that orbit each other. The skies of such worlds would feature double sunsets and complex patterns of light and shadow. Gravitational dynamics make these systems complicated, and stable habitable zones are harder to define. Yet planets in binary systems exist, and some may be habitable despite the challenges. The study of exoplanets is still in its infancy. We have discovered thousands of worlds, but we have characterized only a handful in any detail. For most, we know only their size, their orbital period, and perhaps their mass. Their surfaces, atmospheres, and potential for life remain mysteries waiting to be solved. Each exoplanet is a world unto itself, with its own history, its own geology, its own weather. Some may be barren rocks, blasted by radiation and devoid of interest. Others may be vibrant with life, ecosystems as rich and strange as anything we can imagine. The galaxy is a vast library of worlds, and we have only just begun to read its pages. If life exists on other worlds, how would we detect it? This question drives the search for biosignatures, observable signs that life has altered a planet's environment. A biosignature is not life itself, but the fingerprint it leaves behind, a clue that something living is or was present. The most commonly discussed biosignature is atmospheric oxygen. On Earth, oxygen is produced almost entirely by photosynthesis. Without the continuous activity of plants, algae, and cyanobacteria, oxygen would quickly react with rocks and disappear from the atmosphere. Detecting large amounts of oxygen in the atmosphere of an exoplanet would be a strong hint that something is producing it. Possibly life. But oxygen alone is not proof of life. Certain geological and chemical processes can produce oxygen without biology. Water molecules can be split by ultraviolet radiation, releasing oxygen into the atmosphere. A planet with abundant water and strong stellar radiation might accumulate oxygen without any living organisms. Scientists must consider multiple lines of evidence before concluding that a biosignature indicates life. Methane is another potential biosignature. On Earth, most methane is produced by living organisms, particularly microbes called methanogens, that thrive in oxygen-free environments. Methane is also released by geological processes, so its presence is not definitive. However, The combination of methane and oxygen together would be intriguing. These gases react with each other and should not coexist for long unless something is continuously replenishing them. The simultaneous detection of oxygen and methane in an exoplanet's atmosphere would be a powerful biosignature. Such a combination suggests active chemistry that is out of equilibrium, a hallmark of life. Earth's atmosphere is far from chemical equilibrium precisely because life keeps pumping oxygen and methane into it. Finding similar disequilibrium on another world would demand explanation. Nitrous oxide, sometimes called laughing gas, is another biosignature candidate. On Earth, it is produced primarily by microorganisms as part of the nitrogen cycle. It is a trace gas in our atmosphere, but it could be more abundant on other worlds with different conditions. Detecting nitrous oxide alongside other biosignatures would strengthen the case for life. Some scientists have proposed searching for technosignatures, signs not just of life, but of technology. These could include artificial lights on a planet's night side, industrial pollution in the atmosphere, or megastructures that block starlight in unusual patterns. Technosignatures would indicate not just life, but intelligent technological civilizations. None have been detected, but the search continues. The James Webb Space Telescope is beginning to analyze exoplanet atmospheres in unprecedented detail. By observing transits when planets pass in front of their stars, Webb can detect the chemical fingerprints of gases in the thin sliver of atmosphere backlit by starlight. Early results have revealed carbon dioxide, water vapor, and other molecules in the atmospheres of gas giants. Observations of smaller, rocky planets are more challenging but within reach. One of the first rocky exoplanets studied by Webb is TRAPPIST-1b, the innermost planet of the TRAPPIST-1 system. Initial observations suggest it may lack a substantial atmosphere, perhaps stripped away by the red dwarf's radiation. This is disappointing for habitability, but valuable for understanding how planets evolve around different types of stars. The search for biosignatures requires patience and caution. Even if we detect promising signals, alternative explanations must be ruled out. The history of science is littered with false alarms and premature announcements. The discovery of life beyond Earth would be one of the most profound findings in human history, and it must be supported by overwhelming evidence. Future telescopes will expand our capabilities dramatically. Proposed missions like the Habitable Worlds Observatory aim to directly image Earth-like planets and analyze their atmospheres with enough precision to detect biosignatures. Such observations are decades away, but they represent the next frontier in the search for life. Ground-based telescopes are also contributing to the search. Extremely large telescopes under construction in Chile and Hawaii will have mirrors tens of meters across, gathering enough light to study exoplanet atmospheres from the ground. Adaptive optic systems will correct for the blurring caused by Earth's atmosphere, achieving unprecedented clarity. The search for biosignatures is a search for patterns, chemical combinations that life creates and maintains, anomalies that demand explanation. We do not yet know what we will find. Perhaps we will discover that biosignatures are common, that life has left its mark on worlds throughout the galaxy. Or perhaps we will find only barren atmospheres, chemical equilibrium, and silence. Either answer would reshape our understanding of our place in the universe. While some scientists search for biosignatures, others listen for signals. The search for extraterrestrial intelligence, known as SETI, looks for evidence of technological civilizations, not by analyzing atmospheres, but by scanning the skies for artificial transmissions. If intelligent beings exist elsewhere in the galaxy and have developed radio technology, their signals might be detectable across interstellar distances. The idea of listening for alien signals dates back to the early days of radio astronomy. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a paper suggesting that extraterrestrial civilizations might communicate using radio waves. They proposed searching at a frequency of 1,420 megahertz, the natural emission line of hydrogen, arguing that any technologically advanced species would recognize this universal frequency. The first modern SETI experiment was Project Ozma, conducted by Frank Drake in 1960. Using a radio telescope in West Virginia, Drake listened to two nearby sun-like stars for several weeks. He detected no alien signals, but the project established the methodology that SETI researchers would follow for decades. It was the beginning of a systematic search that continues to this day. Over the years, SETI has evolved and expanded. Larger telescopes, more sensitive receivers, and broader frequency coverage have increased the chances of detecting a signal. The search has moved beyond simple radio waves to include optical signals, brief flashes of laser light that an advanced civilization might use for interstellar communication. The WOW signal remains one of the most intriguing events in SETI history. On August 15, 1977, astronomer Jerry Amon was reviewing data from the Big Ear radio telescope in Ohio when he spotted an unusually strong signal. It lasted for 72 seconds, the maximum duration the telescope could observe a fixed point in the sky. Amon circled the signal on the printout and wrote, "Wow," in the margin. The WOW signal matched the profile of what SETI researchers expected from an artificial extraterrestrial transmission. It was narrowband, meaning it was concentrated at a specific frequency rather than spread across the spectrum. It came from the direction of the constellation Sagittarius, and it has never been detected again, despite numerous follow-up observations. The source of the WOW signal remains unknown. Some scientists have proposed natural explanations, such as a comet releasing hydrogen gas. Others believe it may have been terrestrial interference, misidentified as an extraterrestrial signal. And some hold out hope that it was exactly what it appeared to be: a brief transmission from another civilization. Without a repeat detection, we may never know. Modern SETI efforts benefit from advances in computing power. The Breakthrough Listen project, launched in 2015, is the most comprehensive SETI program ever undertaken. It uses some of the world's largest radio telescopes to survey millions of stars, scanning billions of frequency channels simultaneously. The data volumes are enormous, requiring sophisticated algorithms to search for patterns that might indicate artificial origin. Breakthrough. Listen has not yet detected a confirmed alien signal, but it has identified numerous candidates that required investigation. Most turn out to be terrestrial interference, signals from satellites, aircraft, or ground-based electronics. Distinguishing between human-made noise and potential extraterrestrial transmissions is one of the greatest challenges in SETI research. The search for optical signals has also intensified. A sufficiently powerful laser could outshine its parent star for a brief instant, making it visible across interstellar distances. Such flashes would last only nanoseconds, requiring specialized detectors to capture them. Several observatories now conduct optical SETI searches, watching for the telltale blink of an alien beacon. SETI researchers have also considered what kinds of signals an alien civilization might send. Would they broadcast continuously, or only occasionally? Would they aim their transmissions at specific targets, or broadcast in all directions? Would they use frequencies we have thought to search, or something entirely unexpected? These questions shape the design of SETI experiments and remind us how much we are guessing about the behavior of beings we have never met. The silence of the cosmos is itself a puzzle. If intelligent civilizations are common, Why have we not detected their signals? This question, known as the Fermi paradox, haunts the search for extraterrestrial intelligence. We have been listening for decades and have heard nothing conclusive. The universe appears to be vast, ancient, and silent. Some explanations for the silence are mundane. Perhaps we are not listening at the right frequencies, or in the right directions, or at the right times. Perhaps alien civilizations use communication technologies we have not imagined. Perhaps the distances between stars are simply too great for signals to be practical, even at the speed of light. Other explanations are more troubling. Perhaps intelligent civilizations are rare, arising only under exceptional circumstances. Perhaps they tend to destroy themselves before they can reach out to the stars. Perhaps they exist but choose not to communicate, observing the cosmos in silence. Each possibility carries implications for our own future. SETI is a search driven by hope and curiosity. It requires patience, persistence, and a willingness to confront the unknown. Even if we never detect a signal, the search itself is valuable. It forces us to think carefully about the nature of intelligence, the possibilities of technology, and the place of humanity in the cosmic order. And if we do detect a signal, even a single, unambiguous transmission from another world, it would change everything. The Fermi paradox takes its name from physicist Enrico Fermi, who reportedly asked during a lunchtime conversation in 1950, "Where is everybody? If the galaxy is billions of years old and contains billions of stars, many with planets, then intelligent civilizations should have had ample time to arise and spread throughout the Milky Way. Yet we see no evidence of their existence. The galaxy appears empty." This contradiction between the expectation of abundant life and the apparent absence of evidence is the heart of the paradox. Various explanations have been proposed, each with different implications for the prevalence of life and intelligence in the universe. One possibility is that intelligent life is extraordinarily rare. The steps from simple chemistry to complex civilizations may be so improbable that we are among the first, or the only, species to have made the journey. Perhaps life arises frequently, but rarely evolves intelligence. Perhaps intelligence rarely leads to technology. Each step in the chain might be a filter that most lineages fail to pass. The concept of the Great Filter captures this idea. Somewhere between the formation of a habitable planet and the emergence of a galaxy-spanning civilization, there may be one or more barriers that are extremely difficult to overcome. If the Great Filter lies in our past, if the origin of life or the evolution of complex cells is the hard part, then we may have already passed the most dangerous hurdle. But if the Great Filter lies ahead, it suggests that civilizations tend to destroy themselves before they can spread to the stars. Self-destruction is one commonly proposed filter. Nuclear war, climate catastrophe, engineered pandemics, artificial intelligence gone wrong. There are many ways a technological civilization might bring about its own end. If most civilizations succumb to such dangers shortly after developing powerful technologies, the galaxy would be littered with the ruins of failed experiments, silent and undetectable. Resource depletion is another possibility. A civilization that exhausts its planet's resources before developing sustainable practices might collapse before it can expand beyond its home world. Space travel requires enormous energy and infrastructure. A society in decline might never muster the resources to reach the stars. Some scientists have proposed that civilizations may simply choose not to expand. Perhaps interstellar travel is possible, but undesirable, too slow, too dangerous, too expensive. Perhaps advanced civilizations turn inward, focusing on virtual realities or contemplative pursuits rather than physical exploration. A galaxy full of stay-at-home civilizations would appear empty even if intelligence is common. The zoo hypothesis suggests that advanced civilizations may be aware of us, but deliberately avoid contact. Perhaps they observe humanity from a distance, like naturalists watching wildlife, waiting until we reach a certain level of development before making themselves known. This idea is speculative and untestable, but it illustrates the range of possibilities that have been considered. Another explanation is that intelligent civilizations are common but short-lived on cosmic timescales. The Milky Way is over 13 billion years old, but human civilization has existed for only a few thousand years, and radio technology for barely a century. If civilizations typically broadcast for only a few centuries before going silent, whether through extinction, transcendence, or simply loss of interest, the chances of two civilizations being active at the same time and close enough to communicate might be vanishingly small. The vast distances of space compound the problem. Even at the speed of light, a signal from the nearest star system would take over 4 years to reach us. A signal from the far side of the galaxy would take 100,000 years. If civilizations are scattered across space and time, they might never overlap closely enough to make contact. Perhaps the universe is not silent, but speaking in languages we do not yet understand. Alien civilizations might communicate using technologies beyond our current comprehension: quantum entanglement, gravitational waves, or phenomena we have not yet discovered. Our radio telescopes might be the equivalent of listening for smoke signals in an age of fiber optics. Some researchers have suggested that we might be living in a cosmic backwater, far from the centers of galactic civilization. If intelligent species cluster in certain regions, near the galactic core perhaps, or in dense stellar neighborhoods, then our position in a relatively sparse spiral arm might explain why we have not been visited or contacted. The simulation hypothesis offers a more radical explanation. If advanced civilizations can create detailed simulations of reality, then the number of simulated universes might vastly exceed the number of real ones. In that case, we might be living in a simulation ourselves, which could be designed to appear empty of other intelligent life. This idea is impossible to prove or disprove, but it has gained traction among some philosophers and scientists. The Fermi paradox has no definitive solution. Each proposed explanation raises further questions and invites speculation. What we know for certain is that despite decades of searching, we have found no conclusive evidence of extraterrestrial intelligence. The silence may be telling us something profound about the rarity of life, the difficulty of interstellar communication, or the nature of civilizations. Or it may simply reflect the limitations of our search so far. The paradox reminds us that the question of alien life is not merely scientific, but existential. If we are alone, we bear a unique responsibility as the only minds in an otherwise unconscious cosmos. If we are not alone, we are part of a larger community whose nature and intentions we cannot yet know. Either possibility is humbling, and both demand that we continue searching. If life exists beyond Earth, what forms might it take? Our imagination is shaped by the only example we have: life on our own planet. But the universe is vast and varied, and alien life might be stranger than anything we have conceived. It might be familiar in some ways and utterly foreign in others. It might challenge our very definition of what it means to be alive. The most likely form of alien life, if we find it, is microbial. Single-celled organisms dominated Earth for billions of years before complex life evolved. Even today, microbes vastly outnumber all plants and animals combined. If life follows similar patterns elsewhere, the galaxy may be teeming with microbial ecosystems, bacteria-like organisms in subsurface oceans, archaea-like creatures in volcanic vents, simple cells drifting in alien atmospheres. Microbial life would be a profound discovery, even if it lacks the drama of intelligent aliens. Finding even a single microbe on Mars or Europa would prove that life is not unique to Earth, that the transition from chemistry to biology can happen more than once. It would suggest that life may be common throughout the universe, arising wherever conditions permit. But complex life is another matter. On Earth, it took nearly 4 billion years for multicellular organisms to evolve. And even then, complex life remained relatively simple for hundreds of millions of years before the Cambrian explosion produced the diversity of body plans we see today. The evolution of complexity may require rare circumstances, stable environments, sufficient time, evolutionary innovations that are difficult to achieve. If complex life is rare, the universe might be filled with planets covered in microbial mats, never progressing beyond the simplest forms. Oceans might teem with single-celled organisms while remaining devoid of fish, whales, or anything we would recognize as an animal. This would be a universe rich in life, but poor in complexity. Countless worlds of pond scum, beautiful in their own way, but far from the science fiction visions of alien civilizations. Intelligence is rarer still. On Earth, many lineages have evolved complex behaviors, social structures, and problem-solving abilities. But the kind of intelligence that builds civilizations, language, abstract thought, technology, has arisen only once, in humans, in the last few 100,000 years. This suggests that technological intelligence may be an evolutionary accident, a fluke rather than an inevitable outcome. Some scientists argue that intelligence is convergent, that it will evolve repeatedly because it provides such powerful advantages. Eyes have evolved independently dozens of times on Earth, and flight has evolved in insects, birds, bats, and pterosaurs. Perhaps intelligence is similarly favored by natural selection, arising wherever conditions allow. If so, intelligent beings might be scattered throughout the galaxy, each having found their own path to awareness. Others are more skeptical. Intelligence is metabolically expensive. Large brains require enormous amounts of energy and take years to develop. For most of Earth's history, evolution favored other strategies: speed, armor, camouflage, venom. Intelligence won out in one lineage, but there is no guarantee it would do so elsewhere. Alien worlds might be populated by creatures as complex as dinosaurs, but lacking the spark of self-awareness. If intelligent aliens exist, they might be nothing like us. Human bodies are shaped by the specific conditions of Earth, its gravity, atmosphere, chemistry, and evolutionary history. Aliens evolved on different worlds would face different pressures and develop different solutions. They might have more limbs or fewer, different senses, different metabolisms. They might be aquatic, airborne, or subterranean. They might live as individuals or as collective organisms, distributed minds spread across many bodies. The form of alien intelligence might be shaped by the nature of their world. Beings evolved on a high-gravity planet might be short and sturdy, built to withstand the crushing pull of their world. Creatures from a low-gravity moon might be tall and delicate, adapted to a gentler environment. Life in a dense atmosphere might never develop vision as we know it, relying instead on sound or electrical fields to navigate. Aquatic intelligence is a possibility worth considering. On Earth, dolphins and octopuses have developed remarkable cognitive abilities despite their watery environments. An ocean world might give rise to beings of great intelligence who never discover fire, never smelt metal, never build radio telescopes. Such civilizations might be forever hidden from our searches, brilliant minds trapped beneath ice or waves, unaware that anyone is looking for them. Silicon-based life remains a staple of science fiction, though its plausibility is debated. Silicon can form complex molecules, but it lacks the versatility of carbon. Silicon bonds are less stable, and silicon dioxide, the equivalent of carbon dioxide, is a solid rather than a gas, which would complicate respiration. Still, on a world with very different chemistry, silicon-based life might find ways to thrive that we have not imagined. Life based on alternative solvents is another possibility. Water is essential to life on Earth, but ammonia, methane, or other liquids might serve similar functions on colder worlds. Ammonia remains liquid at much lower temperatures than water and could support biochemistry in environments we would consider frozen. The lakes of Titan, filled with liquid methane and ethane, might harbor life forms adapted to conditions utterly unlike our own. Some theorists have speculated about life forms beyond chemistry entirely. Plasma-based life in the atmospheres of stars, magnetic field organisms in interstellar space, creatures made of pure energy. These ideas push the boundaries of what we consider possible. They are highly speculative, unsupported by evidence, but they remind us that the universe may contain possibilities we cannot yet conceive. Artificial intelligence represents another form that extraterrestrial intelligence might take. A civilization that develops advanced AI might eventually be superseded by its creations. Machine minds could outlast their biological creators, spreading through the galaxy on timescales impossible for organic beings. If such machine civilizations exist, they might be the most common form of intelligence in the universe, patient, durable, and alien, in ways that biological life could never match. The motivations of alien intelligence are impossible to predict. Human minds are shaped by millions of years of evolution as social primates on the African savanna. Our desires, fears, and values reflect that history. Aliens with different evolutionary backgrounds might have entirely different psychologies, perhaps incomprehensible to us, perhaps recognizable in surprising ways. Some scientists have suggested that certain features of mind might be universal. Mathematics, for example, seems to be discovered rather than invented. The same truths hold regardless of who is thinking about them. Beings of sufficient intelligence might converge on similar mathematical and scientific knowledge, providing a basis for communication, even if everything else about them is foreign. Music, too, has been proposed as a potential universal language. The physics of sound, the mathematics of harmony, the emotional responses that certain patterns evoke, these might be shared across intelligent species, even if the specific forms of music differ wildly. The golden record carried by the Voyager spacecraft includes musical selections from around the world, a hopeful gesture toward whatever ears might one day listen. But we should not assume that aliens would be friendly, curious, or interested in communication. They might be indifferent to other species, focused entirely on their own concerns. They might be hostile, seeing other civilizations as competitors or threats. They might be so different from us that meaningful communication is impossible, like trying to have a conversation with an ant or a hurricane. The diversity of possible alien life is limited only by the laws of physics and chemistry, and our imagination. When we search for life beyond Earth, we search not for one thing, but for a vast range of possibilities. We might find microbes or minds, familiar forms or utterly alien ones. The only certainty is uncertainty itself. What would it mean if we made contact with an extraterrestrial civilization? This question has occupied philosophers, scientists, and storytellers for generations. The discovery of intelligent life beyond Earth would be one of the most transformative events in human history, with implications that ripple through every aspect of society. The first and most immediate impact would be the knowledge itself. Confirmation that we are not alone would settle a question that has haunted humanity since we first looked up at the stars. It would prove that the universe is not merely vast and ancient, but also inhabited, that minds can arise in more than one place, that we are part of a larger community of intelligence. This knowledge would likely inspire a profound sense of humility. Throughout history, humans have gradually been displaced from the center of the cosmos. We learned that Earth is not the center of the solar system, that the Sun is not the center of the galaxy, that our galaxy is just one among billions. The discovery of alien intelligence would continue this process, reminding us that we are not the sole inheritors of the universe, but one species among potentially many. For some, the discovery might be deeply unsettling. Religious and philosophical frameworks that place humanity at the center of creation would need to be reconsidered. Questions about the nature of the soul, the meaning of salvation, and humanity's special relationship with the divine would take on new dimensions. Some traditions might adapt easily, others might struggle to incorporate the new reality. Science would be revolutionized. Studying an independent example of life would transform biology, allowing us to distinguish between universal principles and local accidents. We would learn whether the chemistry of life on Earth is the only solution or one of many. We would see how evolution operates under different conditions, what forms intelligence can take, what technologies are possible. If the alien civilization were more advanced than our own, we might gain access to knowledge and technologies beyond our current understanding. Energy sources, medical treatments, materials, and insights into the nature of reality could leap forward by centuries or millennia. The history of Earth shows how contact between civilizations at different technological levels can accelerate development, though it also shows the dangers such contact can bring. The cultural impact would be immense. Art, literature, music, and philosophy would grapple with the new reality. New religions might arise, while existing ones adapt. The shared knowledge that we are not alone might foster a sense of global unity, as the divisions between nations and cultures seem smaller in the face of a larger cosmic community. Or it might exacerbate existing conflicts, as groups compete to control contact or interpret its meaning. First contact scenarios have been explored extensively in fiction, offering a range of possibilities. In some stories, aliens arrive as benevolent teachers, guiding humanity toward a better future. In others, they come as conquerors or predators, viewing us as resources to be exploited. Still, others depict aliens as indifferent, pursuing their own agendas with little regard for the beings they encounter. The reality might be none of these. Contact might come not through a dramatic arrival, but through the detection of a distant signal, a message from a civilization too far away for meaningful conversation. A signal from a star 1,000 light-years away would take 1,000 years to reach us, and our reply would take another 1,000 years to arrive. Such communication would be more like archaeology than conversation, a slow exchange of information across the vastness of space. If contact involved a nearby civilization, the dynamics would be different. Real-time communication would be possible, though even at the speed of light, conversations with a civilization around the nearest star would involve delays of over 8 years between question and answer. Such exchanges would require patience and careful thought, with each message carrying the weight of years of waiting. The question of whether to respond to an alien signal is itself controversial. Some scientists argue that we should listen but not reply, avoiding drawing attention to ourselves until we better understand the nature and intentions of other civilizations. Others believe that any civilization capable of detecting us probably already knows we are here, given the radio signals we have been broadcasting for over a century. The debate reflects deeper uncertainties about the risks and rewards of contact. Protocols for contact have been developed by international organizations, though they have no binding authority. The SETI community has agreed on guidelines for verifying and announcing a detection, emphasizing transparency and international cooperation. But no government or institution has the power to speak for all of humanity, and the question of who should respond and what they should say remains unresolved. Some researchers have crafted messages intended for extraterrestrial recipients. The Arecibo message, transmitted in 1974, was a brief radio signal encoding information about human biology, our solar system, and the structure of DNA. The Voyager Golden Records carry sounds and images from Earth, a message in a bottle cast into the cosmic ocean. These efforts are largely symbolic, but they reflect a deep human desire to reach out, to make ourselves known, to connect with whatever else might be out there. The discovery of alien life, whether microbial or intelligent, would force us to reconsider our place in the universe. It would challenge assumptions, inspire new questions, and open possibilities we cannot yet imagine. It would remind us that the cosmos is not a dead expanse of rock and gas, but a place where minds can arise, where life can flourish, where we are not as alone as we sometimes feel. As we near the end of this journey, let us pause to consider the cosmic perspective, the view that emerges when we step back and see ourselves within the vastness of space and time. This perspective does not diminish us. Rather, it reveals the extraordinary nature of our existence and the profound mystery of being here at all. We live on a small rocky planet, orbiting an ordinary star in the suburbs of an average galaxy. Our star is one of hundreds of billions in the Milky Way, which is itself one of trillions of galaxies in the observable universe. The light from the most distant galaxies has traveled for over 13 billion years to reach us, crossing a universe that has been expanding since the Big Bang. On the scale of the cosmos, human civilization is a fleeting moment. The universe is approximately 13.8 billion years old. Earth formed about 4.5 billion years ago. Life appeared soon after, but complex animals have existed for only about 500 million years. Humans emerged a few 100,000 years ago, and recorded history spans barely 5,000 years. Our entire technological civilization, with its radio telescopes and spacecraft, is less than 2 centuries old. In cosmic terms, we are newborns, just opening our eyes to the universe around us. We have taken our first tentative steps beyond our home planet, sending probes to the outer reaches of our solar system and astronauts to the moon. We have detected planets around other stars and begun to analyze their atmospheres. We have listened for signals from the darkness and contemplated the possibility of other minds. The universe does not owe us meaning. It operates according to physical laws that are indifferent to our hopes and fears. Stars are born and die. Galaxies collide and merge. Black holes consume matter and warp space, all without regard for whether anyone is watching. In this vast, impersonal cosmos, life is a rare and precious phenomenon, and consciousness rarer still. Yet here we are, improbable collections of atoms that have organized themselves to ask questions about their own existence. We are the universe contemplating itself, matter that has awakened to wonder. Every element in our bodies was forged in the hearts of ancient stars that exploded billions of years ago, scattering their ashes across space to eventually coalesce into new worlds and new forms of complexity. The search for alien life is, in a sense, a search for cosmic companionship. We want to know that we are not alone, that the universe has produced minds beyond our own, that the spark of awareness has kindled elsewhere in the darkness. This desire is deeply human, rooted in our nature as social beings who find meaning in connection. If life is common in the universe, we are part of a grand community, one of countless experiments in consciousness scattered across the stars. The universe would be revealed as a place where mind emerges readily, where the transition from matter to awareness is a natural outcome of cosmic evolution. We would have siblings in the darkness, fellow travelers on the journey of existence. If life is rare, our responsibility is greater. We might be among the first minds to arise in this corner of the cosmos, pioneers in a universe still waiting to be explored. The choices we make, the values we hold, the future we build, all would take on heightened significance. We would be custodians of something precious, a flame of awareness that might be unique in all the vastness of space. Either possibility is profound. Either way, we are connected to the cosmos at the deepest level, made of its substance, governed by its laws, participants in its unfolding story. The atoms in our bodies have been part of stars, part of interstellar clouds, part of countless transformations over billions of years. We are not separate from the universe. We are expressions of it. The night sky, seen from a dark location far from city lights, offers a glimpse of this cosmic context. The Milky Way stretches overhead, a river of light composed of billions of stars too distant to see individually. Each point of light is a sun, potentially with its own family of planets, its own possibilities for life. The sky is not empty. It is full of worlds. Ancient humans looked at the same stars and wove stories about what they saw. They imagined gods and heroes, animals and journeys, written in the patterns of the constellations. We have replaced those stories with scientific understanding, but the sense of wonder remains. We know more than our ancestors, yet the mystery has only deepened. The question of whether we are alone touches something fundamental in the human spirit. It is a question about belonging, about meaning, about the nature of existence itself. We may not answer it in our lifetimes. We may not answer it for centuries. But the asking itself is valuable, a testament to our curiosity and our courage in the face of the unknown. Tonight, as you rest, the universe continues its ancient rhythms. Stars are forming in distant nebulae, collapsing from clouds of gas and dust into new points of light. Planets are drifting in their orbits, some warmed by their suns, others frozen in darkness. Somewhere, perhaps, life is stirring. Microbes dividing in alien oceans, creatures swimming through underground seas, minds pondering questions not unlike our own. We cannot know for certain what is out there. We can only wonder and search, and remain open to possibilities beyond our imagination. The universe is under no obligation to make sense to us, yet it has given rise to beings capable of seeking sense, of asking questions, of looking up at the stars and feeling awe. You are one of those beings. You are a brief arrangement of matter and energy, a pattern of information that has somehow become aware of itself. You are connected to every atom in the cosmos, forged in the same stellar furnaces, obeying the same physical laws. You are the universe experiencing itself, a way for the cosmos to know that it exists. And now, as this journey draws to a close, let your thoughts grow quiet. Let the questions settle like dust after a journey, no longer demanding answers, simply present. The mystery of life in the universe will still be there tomorrow, waiting for those who wish to explore it. For now, there is nothing you need to do. The stars above are older than anything on Earth. Their light has traveled for years, centuries, millennia to reach your eyes. When you see a star, you see the past, a glimpse of how things were long before this moment. The universe is full of such time travelers, ancient light carrying messages from distant eras. If life exists elsewhere, it too is part of this cosmic tapestry, threads woven into the same fabric that holds us. We are not isolated beings on a lonely rock. We are participants in a vast and ancient story, one that began with the first moments of the universe and continues to unfold in ways we cannot predict. Perhaps one day we will find the answer to the question that has guided us tonight. Perhaps we will discover microbes on Mars, or detect biosignatures on a distant exoplanet, or receive a signal from a civilization beyond the stars. Or perhaps we will search for centuries and find only silence, learning that we are rarer and more precious than we ever imagined. Either way, the search has value. It teaches us about the cosmos and about ourselves. It pushes the boundaries of our technology and our understanding. It reminds us that there are still mysteries to solve, still frontiers to explore, still questions worth asking. For now, let these thoughts fade into the background. Let your breathing slow, your body relax, your mind drift toward rest. The universe will keep its secrets for another night, and you will keep your place within it. A small warmth in the darkness, a spark of awareness in the vast and ancient cosmos. If you are still awake, you can go ahead and watch the next video now. But if your eyes are heavy, if sleep is calling, then let yourself go. There is nothing more to do, nothing more to think about. Only rest, only peace, only the gentle pull of dreams. Thank you for joining me on this journey through one of humanity's oldest questions. I hope it has brought you a sense of wonder, a moment of calm, and perhaps a new way of looking at the night sky. Sleep well, dream softly, and remember, you are made of stardust, and you belong to the cosmos. Good night.